The lecture tonight is about computer architectures, and what I want to do is I want to tell you a bit about the beginning of computing, which of course started in Cambridge. I knew this was going to happen. Well, one of the beginnings was in Cambridge with the EDSAC after Manchester finished the baby there. We have a period of great British home computers that I want to talk a little bit about. Then, having been around for a while and stepping back, I felt that there were 5 distinct waves of computing that I want to quickly tell you about. And it's quite interesting to stand back and view it as waves, because then you can discern the individual properties that the waves themselves had. And I want to tell you a bit about that. How these waves clash, because they actually don't like to coexist. New waves normally kill the old one. A little bit about Intel versus ARM, since this is one of those wonderful David and Goliath stories, and then end up with a couple of slides on what next. So the beginning, if one takes this view, living in Cambridge, of computing was, of course, the EDSAC on the 6th of, which ran on the 6th of May, 49. The one thing that we can say, though, is that it was the first computer that was really used as a computer service regularly. So in that sense, I think we can say that we were the first computer service in the world. Now we're rebuilding EDSAC, as some of you may know. David Hartley, who is here tonight, organized this, and we also have Chris Burton here, who actually helped with the rebuilding of the Manchester baby, and he's already given us invaluable advice on how to rebuild the EDSAC at Bletchley Park. And I went to the kickoff meeting there and was just delighted to see that for the first time, I think in history, we now have a circuit diagram of the EDSAC, because Morris, of course, never bothered to write down the circuit diagram. And if he had, it probably wouldn't be accurate anyway, because he changed his mind during building it. We also have a great leader for the replica project in Andy Herbert, who is, many of you know from the computer laboratory in Cambridge, and he was head of Microsoft research in Cambridge. And he is a very enthusiastic rebuilder of aeroplanes and computers. So I think the project has gotten off to an excellent start. Because in addition to the circuit diagrams, we also have a software emulation. So we know something that Morris didn't. And we know that this computer will work. So the period of the EDSAC was 49 to 58. It's actually short, it's an acronym, stands for Electronic Delay Storage Automatic Calculator. Note that it was called a calculator, not a computer, because what Morris called the computer, we would now call the ALU. So it was actually a calculator. And the reason why it was a calculator, I presume, was, and David Hartley will put me right if I get this wrong, that his mission in life was to provide mathematical tools to the university, and he felt that a computer would be a good mathematical tool for researchers to have. And indeed, I think 2 Nobel laureates mention the EDSAC as an invaluable tool that contributed to their Nobel Prize. We also had an outstandingly gifted programmer in David Wheeler, who is widely recognized as the inventor of the subroutine. And this is a picture of the EDSAC. Here you see a young Morris kneeling at the mercury delay line, and during that presentation that Chris gave at Bletchley Park at the beginning of the EDSAC program, for the first time I understood how the detailed architecture of this computer, which of course is a serial architecture, it's a bit serial machine. What I hadn't appreciated was that every bit, the only storage that this computer had was actually the mercury delay line. There was no other way of getting data. So if you wanted any datum, You had to wait until it came round again on that mercury delay line. So although, again, to my surprise, this machine ran at a megahertz, which was only half as fast as the BBC Micro many years later, the megahertz was on a bit serial machine where you had to wait for the bits to come round on a mercury delay line when you wanted to have a new calculation or a new datum. So the actual number of instructions per second was surprisingly low. It was just 650, given that it clocked at a megahertz. It was not a lot. However, if you compare that with the computing devices that existed before, it was probably the largest step increase in computing power ever, and probably will be the largest step in compute power ever, because the step was 1,500 times. So if you look at Moore's law, or indeed, as I'll tell you later, the invention of the ARM, in terms of the increase in performance of comparable chips, the ARM, I think, was outstanding in achieving a factor of 20 over the Z80 at the time, but this was a factor of 1,500. So quite an interesting event. Now, if you allow me, I'll talk a little bit about the British home computer period, because we were leading the world in home computers at the time with the Sinclair ZX80, I should say, not Z80. The Spectrum that was produced by Sir Clive Sinclair, the Acorn computers, the Atom, the BBC Micro, and later the Archimedes, and of course the ARM spin-out from Acorn later on. But what people often forget now is that there were many, many other computer companies in Britain at that time. There was a thing called a NASCOM, NASCOM 1 and NASCOM 2, that we compared ourselves to at Acorn. There was the New Brain that we beat to the BBC contract. There was a Welsh machine called Dragon. There was the Jupiter Ace, which was a fourth machine. There was Tangerine, Auric 1, Tadpole Torch, and many more that I can't remember anymore. So here are two iconic computers at the time, the ZX80 and the Spectrum, from Sinclair, and of course, by far the best machine at the time, the BBC Micro. Now, why was it the best machine at the time? Do I have a slide on that? Yes. If you compared it with arguably the leading American machine, which was the Apple II, the Apple II ran at 1 megahertz. We ran twice as fast, so that's a factor of 2 right there, not to be sniffed at. We had 32 kilobytes of RAM, which was a lot, and 32 kilobytes of ROM. We had color. The Apple was monochrome. We mixed text and graphics on a single screen. The Apple couldn't do that. And we had something that no computer had at the time. We had a network connection. In fact, Acorn never produced a fully fledged keyboard computer without a network connection. And we had 10,000 installed Econnets in British schools before people knew how to spell Ethernet. So we were leaders in arguably all of these different areas. In addition to that, we really had outstanding software. We had BBC Basic, which was shown off to Bill Gates when he visited us and tried to sell MS-DOS to us. We had an Acorn OS, which was an operating system. And one of the things we could point out to Bill Gates is that we couldn't take such a retrograde step as adopting MS-DOS, because we actually had an operating system that was worth the name operating system, which MS-DOS certainly wasn't. And by the way, we could tell him that if you sat in front of a BBC microcomputer as a child in a British school, you could type *I am Johnny, and you would be logged on to the local area network through the Econet, and you could download files from the file server with load and store and save commands as if it was from the local floppy disk. And when I pointed this out to Bill, saying that you could download this thing from the file server over a network, Bill's response was, "What's a network?" So we were in the lead, especially on the networking side. So you might well ask, why is the world not Acorn compatible? Why is it Microsoft compatible? Well, we missed out on a trick, and that is willingly licensing either the Ethernet or our basic, or indeed the operating system, to other companies. This was just not a business model that we even entertained. We thought that this was our competitive advantage. We wanted to keep this ourselves. Commodore, for example, approached us asking if we would license the Ethernet to them to establish a standard, which we could have. And of course, later on, the Ethernet was pinched by Apple and called Apple Talk. So, but we were really the first ones to do that. The other thing that we did, which was, of course, very much what the BBC wanted, was to have a product that could be easily expanded. So we had every interface that you could imagine at the time. We had HDD converters, we had serial interfaces, parallel interfaces, and a 1 megahertz bus where you could put a second processor onto the BBC Micro. Chris Curry, my partner at Acorn, then produced a bit of a marketing coup by convincing the BBC to put their name on our computer and run at first a 10-part and later a 30-part series on computing. And it's sort of difficult to remember this, but I see some people, enough white hair here in the audience to, those of you would at least remember this, that people would come home from having a beer at the pub at 6 o'clock because they wanted to watch the computer literacy program, called the computer program. It was just fascinating at the time. The whole nation was excited about the chip, as they called it, because the first program was actually called the chip sedan. They didn't actually call it a microprocessor. They called it the chip. And there was this, the BBC told everybody there will be more than one chip in your home in the future. Little did they know. There will be tens and now probably hundreds, because I think the last count was that you have around 50 in most of your cars alone. And it was just very, very popular and led to arguably to a generation of programmers in this country that created the British software industry. And I'm just so pleased that Eric Schmidt gave a talk at, I think it was at Glasgow or at Edinburgh not too long ago, saying that Britain had a lead with the BBC Micro teaching pupils how to program, and what a shame it is that we squandered this lead because we changed our curriculum from teaching people how to program to teaching people how to work Word and Excel and PowerPoint, which, you know, anybody with half a brain can probably pick up just over the by using it or having some internet help with it, whereas programming, I think, requires a little bit of help from teachers. So we now have a new initiative, which in fact was recommended by Steve Ferber, who is with us tonight. He wrote a very important recommendation on that, which I think has now been accepted, and hopefully there will be changes in the curriculum soon to reintroduce programming into schools. So now the 5 waves of computing. They are, of course, the mainframe, the minicomputer, workstations, the personal computer, and now, surprisingly, the phone. Who would have ever thought that the phone will become a major computer platform? But it has, especially in connection with the cloud. So the mainframe, and I dug out some sort of iconic computers that characterize each of the waves. And the iconic mainframe, I suppose, was the IBM 370. I remember using that computer at Cambridge University. I also remember that a 4 megabyte upgrade arrived whilst I was doing my PhD. Lots of people questioned the wisdom of having so much memory because they wouldn't know what to do with it. Now this, of course, was not a memory for a single user. This was memory for 200 users that were at the end of teletypes there. The other interesting thing to note, and you might remember films and newsreels and BBC news on that, whenever you saw a picture of a computer, the key thing that you always saw were the turning tapes, because that sort of defined a computer, because it was the only thing that moved. So there was homed in on that. So what characterized mainframes? Well, they were quite expensive. They were typically $1 million or more. There were very few of them, only a sort of 1,000 per year, although many of you know the famous Watson quote, who was the head of IBM at the time, who said there might be a maximum market of 6 for them in the world. Well, he got that wrong. They were all multi-user. They lived in air-conditioned rooms. The way you interacted with them was through teletypes. There was no network. And I remember during my PhD at the Cavendish, I'm a physicist, not a computer scientist, as many of you will know. We were trying to predict. We knew about Moore's law, we knew about miniaturization, so we were trying to predict what computers will look like in 10 or 20 years' time. And our idea of a really miniaturized IBM 370, we decided was a thing that looked like the bit that we used to wipe the blackboard. Because we argued that we had to have an output device, and the smallest output device that you could think of was a printer that would run along the paper to print out the printout that we normally got on teletypes. It didn't occur to us that the sensible thing is actually to have a VDU that would be giving you real-time output, because that just wasn't used at the time. The way you got the output is the output was printed. Now, the thing that I want to point out in particular on this slide and all the subsequent slides is the use case. Because these use cases really defined the computer at the time. The use case was central government departments for sensors or calculating shell trajectories, headquarters of large companies to do the accounting, and of course science to do scientific calculations. The central processing unit, of course, was made out of discrete components, often bipolar or ECL at the time. And there was very soon a dominant company, IBM. To start off with, IBM had 7 sisters. After that, it became the bunch. But really, IBM dominated this wave. And this is a wave characteristic. If you look at all the subsequent waves, towards the end of the wave, you always have some dominant companies. And often you also get a lock-in, that these dominant companies become dominant because they become quasi-monopolies on the back of often some interface specifications, as was the case with the DASD disks. I remember Rob Wilmot complaining bitterly to me that ICL will never be able to make any inroads on the IBM stranglehold because of the DASD disk specifications. And of course, they had it all. They were the vertically integrated company. They took the sand off the beaches, made the chips, made the circuit board, designed the chips, made the circuit boards, wrote the software, wrote the operating system, invented the languages like COBOL and Fortran, delivered the machine, serviced the machine, and finally took it away from you at the end of the period to scrap it as well. So it really was a soup to nuts thing. And then came the Minicomputer. And again, there was, in the end, a dominant company with DEC, with an iconic product called the VAX 780. As you see, it was a lot smaller, and some VDUs started to appear as well. They were very expensive, and they weren't very good, but at least you had some immediate idea of what was going on in the computer. They were a lot cheaper than mainframes, and therefore there were a lot more of them. But look at the use case again. It was still multi-user, but now universities could afford them, and maybe even university departments rather than just the computer laboratory. Smaller companies could have their own computer, and engineering companies could have it. And the CPUs weren't made out of discrete transistors anymore, but of course this was the age of the 7400 series of MSI components. The dominant company, of course, was DEC with the VAX, and there was also the rise of the Ethernet, that these computers were actually networked together. And some of you might remember the amazing cables, that the DEC cables, they were about a centimeter thick, and the way you connected to your Ethernet was actually through a connector that pierced the insulation, and there was a very thick copper wire in the middle, and you would ram the spike into that copper wire, and that's how you made the connection to the DEC Ethernet at the time. So it was a great period, but this Minicomputer wave also shows a typical wave characteristic, that the dominant company in one wave so far has never become the dominant company in the subsequent wave. And a particularly sad example, of course, is DEC, because DEC was probably the most fabulous computer company at the time. They employed all the smartest people. They had a dominant market share. And when they went down, they didn't go down because they became incompetent. They remained the best minicomputer company in the world. The problem was people stopped buying minicomputers because there was a new belle de jour called a Workstation, and this was the iconic product of that era, the SPARCStation. Now, why did people buy the SPARCStation? Well, they were a lot cheaper. Again, there were many more of them. So the use case expanded dramatically to now engineering, but almost personal engineering. People would have these workstations, as the name suggests, on their desks. They were single user. And after a period of shakeout again, there were companies like Apollo on the East Coast and then Sun on the West Coast. It was really Sun that became the dominant supplier. There was also a revolution in CPU design with RISC, the famous SPARC processor. A dominant operating system arose with Unix and partially new technology from Microsoft. But one of the great revolutions was the CRT, and they were known as 3M machines at the time. Ridiculous looking back. 1 megapixel, so it's 1,000 by 1,000. That's still impressive, although at that time, of course, it was all monochrome. 1 megabyte of memory, incredibly small by today's standards, and 1 MIP of performance. Storage became, there was a revolution in local storage with hard disks, of course, and networks, again, were very important. But the fourth wave did to the Workstation what the Workstation did to the Minicomputer wave. It obliterated them. And it was, if I may bring up this slide, the BBC Micro, that was an iconic product in personal computing, although they weren't called personal computers at the time. At the time of launch of BBC Micro, they were called home computers. And again, same story. A lot cheaper, $1,000 now, roughly. Sold in the hundreds of millions. And the use case really was personal computing, characterized really by 3 main productivity tools: Word, VisiCalc to start off with, and Excel, and PowerPoint. And now, of course, internet browsing is probably the number one use case. We're desktop machines, and again, after a shakeout, during which IBM became the only company to be dominant in 2 waves, albeit not subsequent waves. So for a while, IBM dominated the PC business before they sold it off to Lenovo in China. But we do have a dominant duo in the personal computer wave, sometimes called Wintel. That's Microsoft and Intel, of course. And the dominance here, interestingly, isn't described as a dominance in the manufacture of a computer, the supply of the computer itself. It's a dominance. It's the dominance in 2 components: the microprocessor, where Intel has more than 80% market share, and Windows, where Microsoft has a more than 90% market share. Although there is this peculiar company called Apple, who are the only remaining personal computer producer who actually understand what they're building. It's the truth. Let me tell you the Dell story, as told by Clayton Christensen. And you can find his talk. He's a very famous Harvard professor, wrote a very important and seminal book called The Innovator's Dilemma, on how people, if they really innovate, have to blow themselves out of the water every now and then by new breakthroughs, and how very, very few companies manage to do that. But he's got a new interesting story, and that's the Dell story. It's the Dell ASUS story. So ASUS was a sub-assembly supplier to Dell, and they came to Dell one day and they said, you know this motherboard that you produce, we can produce this motherboard 20% cheaper, and it's not your key your key competence. We can do this cheaper and better. And by the way, you don't need a manufacturing plant anymore. You give this to us, so your return on equity goes up because your assets are now smaller, so you can improve your share price. And the finance guys looked at that and says, this is a good deal. We can buy something 20% cheaper. We need less money to build it because now we don't need a factory. Our profitability goes up, and indeed it did, and the share price went up. And this story repeats itself 4 times, because then they say, look, we're now doing the circuit board for you already. Why don't we do the case for you as well, and then we integrate it all, and we produce the whole thing for you. Except the 5th time, they came back and told exactly the same story. 20% cheaper, we'll do it for you, but they didn't call on Dell. They called on Best Buy and Walmart. So what he reports is that every time the financial guy said, this is a good deal, this is what Harvard Business School tells us we should do, we should increase the return of investment to our shareholders, and yet it hollowed out the company. Dell does not really understand what is in their computers anymore, because they've, of course, apart from outsourcing all the assembly, they've outsourced the microprocessor to Intel, so they don't know what the microprocessor is all about, and they outsourced the operating system to Windows, so they don't have a clue what the operating system does. They just make sure that it runs on their machines. The one amazing exception is Apple, who produce their own processor, of course ARM-based, and they have their own operating system. So that's why they can make such a compelling product that is gaining market share. However, the iconic PC, of course, is the IBM PC. And here is the amazing thing looking back. Some of you might remember. Who remembers the storage capacity of the floppy disk?
640K.
Double-sided, right? I got to 320K, I think. So both of them would give you, say, 600K. This is not enough to store a single picture that we take with our mobile phones nowadays. Now, isn't that a remarkable fact? So, in the same way that these previous waves always got blown out of the water by the subsequent waves, my prediction is that these smartphones plus the cloud will do to the PC what the PC did to the workstation, what the workstation did to the minicomputer, and what the minicomputer did to the mainframe. And here it is, the smartphone, held by a very smart man. It's very sad that he's gone a little bit too early. He wasn't the most amiable guy to meet, but boy, was he smart. And here are the smartphones. The price has fallen further. In fact, it has fallen to 0 if you buy a mobile phone with a contract. The units have again increased almost by a factor of 10 over the previous wave. We're selling about 300 million PCs, and it's last year I think was 1.3 billion, so it's a factor of 4 higher than the previous wave. The use case has extended to voice now. Who would have ever thought that we'd talk to the computer if we wanted to talk to other people, but that's what we do in a smartphone. It covers the internet just as well as PCs now in terms of browsing the internet. It can do video. It really can do everything that a PC can do, and most of it well enough. In the same way that the PC killed the workstation, not when it reached the same capabilities of the workstation, but when it was good enough, when it could do most of the things that the PC, that the workstation could do. And so it is with the smartphone. It's good enough to do a lot of the web browsing, which is the number one use case of the PC. And of course, if you watch especially young people, what they do with their smartphones, they don't make calls. They either text or they use the internet or Facebook or Twitter on it. For a while, there was a dominant European company, Nokia. Sadly, just last quarter, Nokia was overtaken by Samsung as the main provider of phones in the world. But we have this very unexpected appearance of Apple here that had a minor market share in the PC business, but now has a major market share in the smartphone business, especially when it comes to profits that you might make with such smartphones, where Apple is still the leader, although Samsung is the volume leader. There is, delightfully, a standard CPU for smartphones, in fact, all phones, with a 95% market share, and that's, of course, the ARM RISC processor. In terms of the hardware architecture, it is important to note, and that is really the main reason why I think Intel has such a hard time with ARM, is that the PC was dominated by the microprocessor. In fact, people would buy a PC because it had a 3 gigahertz Pentium rather than a 2.8 gigahertz Pentium. So even what seems a trivial difference, really, made the difference in the buying decision. When you buy a mobile phone, you normally don't know what megahertz or gigahertz rate the processor runs on. That's not important. By far more important is the use case, the user interface, touch. And if you look at the hardware architecture underlying it, it's actually these guys that are much more important. It's the baseband processor, it's the connectivity, it's GSM, 3G, HSDPA, which is the data thing for the data channel for the 3G connections, and LTE, curiously, called long-term evolution, more widely known as 4G, has fantastic capabilities. They're completely new companies that appeared because of the importance of the baseband processor and the radio connection. It is actually companies like Qualcomm, a UK startup from Bristol called Icera that has the world's first high-quality soft modem, now bought by NVIDIA, and I think the combination of NVIDIA and Icera might well give Qualcomm a run for their money, Qualcomm being the dominant company in baseband processors. Infineon, bought by Intel because they realized that their microprocessor business is going to go away, and they have got to find a way of selling chips, which is what they're very good at. And the only chips that people buy in this market are the baseband processor chips. People do not buy microprocessors in the phone market, which is the reason why ARM is doing so well. They license them. So here is a smartphone on steroids. It is exactly the same architecture. There is really no difference between an iPad and an iPhone, say, with the exception of the size of the display. And even the connector is the same, as you know. So this architecture is making its way now from a thing that you hold to your ear to a thing that is so good at browsing that it is serious competition for the PC. And as you see here, your speaker is doing his main presentation out of an iPad, out of a tablet, thereby usurping one of the use cases for a PC. I don't need a laptop anymore. I can do this out of my tablet. And Apple, again, has done a superb job in providing the usual productivity software like Pages, Keynote, and Numbers, I think it's called, rather than Word, Excel, and PowerPoint. So these waves clash. Why do they clash? And why is the new wave always winning out the old one? Well, always higher volume, therefore lower price. New wave reaches old wave performance, or close enough, and then there are new and much more exciting use cases. It's these new users that give it the great excitement and the ability to be victorious over the previous wave. We've been through the workstation versus PC story, and now comes the PC versus smartphone story. Because smartphones, I just put up smartphones there as a sort of as a tag for this new wave, but this new wave has smartphones as its main proponent at the moment, but the architecture behind the smartphone is conducive to lots of different package stories. So it can be the iPad, it can be e-readers, it can be a phone, but it can be lots of other things that will appear, especially in the health sector as we go forward. The CPU is good enough and not so central anymore to the success of these new components, but the user interface is. So we've just seen a revolution in the user interface and the way we interact with computers, away from the keyboard and the mouse to a touch interface. And I think a similar thing is just about to happen to voice and eye tracking. We have a very interesting investment in a Stockholm-based company called Tobii, which is the world's leading eye tracking company. And eye tracking is just one of the key ways in which humans indicate to each other that they're paying attention or who they are talking to. And it's a very clever way of handing off the talk token, although it doesn't work with everybody. Then there are SD cards, which is a new way of storing things. So who would have thought that you could have a 32 gigabyte SD card, which you can buy at Tixons at the moment, when the IBM PC had 320 kilobits of floppy storage just a few years ago. But the most surprising thing, I must say, that came left field that nobody predicted was this last line. Who would have thought that Apple can produce an application platform that extracts 350,000 applications? And Google, not to be outdone, Android is actually now shipping more smartphones than Apple and is producing 250,000 apps, and they're actually growing faster than the Apple App Store. Here is the Intel versus ARM story. It's also a RISC versus CISC story, a reduced instruction set computer versus complex instruction set computer. We actually looked at lots of different processors at Acorn to follow the 6502, which we used at BBC Micro. And we actually quite liked the 16032 from National Semiconductor and had a second processor based on that. We also looked at the 68000. We looked at the 8286. And actually did talk to Intel about using that, but they used both. They put both the data bus and the address bus out on the same pins, so we felt that nobody could make a sensible computer out of that because you couldn't get enough bandwidth. You weren't making good use of the memory bandwidth. So we went to Intel and said, well, if you sold us just the core and we had a different pinout, maybe we could make something of your chip. And they said, well, get lost. So we said, well, you get lost, we'll do our own. And that is the only reason why the ARM existed. I remember Steve Ferber and Sophie Wilson going to Western Digital to check out what they were doing in terms of a follow-on to the 6502. And I think they came back much encouraged that these guys there weren't any smarter than we were. So we could actually produce such a chip. And then my major contribution to the ARM project was to give the ARM team two advantages that neither Intel nor Motorola nor Semiconductor ever gave their design tool teams. And those two advantages: one, no people. So it's the only processor that I know in the world that was actually created by just two people, plus then later on the glorious 12 who founded ARM, implementing it, but the actual architecture was done by by 2 people. And the second great advantage was I gave them no money. So there was no way they could produce a very complex chip. It had to be very, very simple. The interesting thing was because the people who did it were rather gifted, they produced one that was very simple, but at the same time had very high performance. So it actually had the same number of transistors as the Z80, which was the leading 8-bit microprocessor at the time, but it had 20 times the performance. So just because of the architectural brilliance of the design, we managed to get 20 times the performance out of the same number of transistors. It's, I think, quite a rare event. Now, there was a completely unintended side effect, and that is we held the world record of MIPS per watt. We weren't producing this chip to be low power. We were producing it to be high performance and low cost. But the BBC was microprocessor, the follow-on products called Archimedes, were mains-powered computers, so they didn't need low power. It was a side effect. But Nokia knocked on the door and said, this is rather useful for our telephones, our mobile phones. And Robin Saxby, who at that time then ran ARM, grabbed this opportunity and established ARM as the standard microprocessor in mobile phones with a 95% market share. This year we're going to sell 8 billion ARMs. That's more than people on Earth and more than Intel has sold in its entire history. We have the ambition of selling 100 billion of them over the next 10 years. You might think that this is ambitious, but if you think about the wave that is about to hit us, which is the Internet of Things, this could well be a factor of 10 more per year than was before. It's also become the most valuable company we have produced in the Cambridge cluster, which with over a $10 billion market cap. And in the year 2010, which is now 2 years ago, interestingly, the value of the ARM chips that we collect a royalty on has overtaken Intel sales, which is over $40 billion. So even in dollar terms, ARM has now become a more important architecture than Intel. Now, why is Intel having this problem with ARM? And the interesting thing is exactly the same story as the DEC story. Intel has not become an incompetent microprocessor company. In fact, it must be said, they are still the best microprocessor company in the world. There is no doubt about this. The problem is, people are not buying microprocessors in the smartphone field. So however smart and good their microprocessors is, if there is no market for microprocessors in this fifth wave, they've got a problem. And the problem is the business model, nothing to do with the processors. And the business model is that people like to license the processors in the mobile phone business, not to buy the chips. So they've got to find a chip that people might want to buy in the mobile phone business. And of course, that's exactly what they've done by buying Infineon. And they're making good inroads into that market as the baseband processor. Interestingly, of course, the chips that they're selling into this market with Infineon has an ARM processor in it. So it's the PC standard versus the mobile standard. This sometimes is depicted as a fight, a David and Goliath fight of ARM versus Intel, but that's actually not the case. It is Intel versus the world, because these are the ARM licensees. And there is not a single there isn't a single semiconductor company of any note in the world that doesn't have an ARM license. There are over 200 for them, and this is just a selection of them. So what next? Well, my prediction is that the mobile phone architecture will win out over the PC architecture for all the reasons that I've repeated a number of times now on my wave argument. Mainly the much wider use case than the PCs and many more apps. And the big question is, will Intel and Microsoft play a role in this new wave and this new standard? And the answer to this question is not clear. The one thing that we can say is that Intel is one of the smartest companies in the world, one of the best run companies in the world, and has, without a shadow of a doubt, the best processing capability in the world, which of course was always financed by the excellent margins that they achieved selling Pentiums in the PC business. So I would not be surprised if Intel manages to do the same as IBM did, because when the mainframe market ceased, IBM didn't seize. IBM reinvented itself as a service company, and my prediction is that Intel will reinvent itself as a chip company that produces chips for this market, and as I said, it's probably the baseband processor. Microsoft is an equally well-run company with 40 billion of cash, so they can wait a little while and come from behind as they always have. And their pact with Nokia is not to be written off. The Windows phone operating system and the Nokia phones are really very nice phones indeed, although they still haven't caught the imagination of people the way that the iPhone has. And there will be many more device categories. So the reason why I've called this the mobile phone architecture is to stress the architecture. You'll find this architecture in lots of different form factors, not just the mobile phone. But my prediction is that it will kill the PC architecture because you don't need such a heavyweight architecture for most of the things that we want to do going forward, especially if you have the backup from the cloud, and it will kill Intel's microprocessor business. So what next? Well, we've got a very interesting initiative using 1 million arms in Manchester in Steve Ferber's Spinnaker project to simulate 1 billion neurons. Now, why is this a sensible thing to do? Well, if you look at what we've done with microprocessors in the past, what I call maybe the Intel program, Intel has produced heroics when it comes to coping with the mismatch of processor speed and memory availability. So if you look at a typical computer, which has an Intel processor in the middle, you will find there's so much memory that is idling most of the time, and a poor processor in the middle that is going flat out, and the whole architecture with now 3 levels of cache is there to redress this imbalance between the number of processors and the number of memory elements. Now, there is, of course, an existence proof that a completely different architecture in the brain, where every neuron is both a storage element and a processing element, has certain advantages in some applications. So to redress this balance and understand what might make multiple processors, a very large number of processors, work well, where most of the time, most of the processors might not do anything, might be idling. But if you need them, they are there with a very low interrupt latency, because one of the problems with the present architecture, of course, is that the interrupt latency, especially if you've got 3 levels of caches, is pretty bad. Same thing is true for energy consumption. If you had asked Henry Ford what the best way of putting a wheel on a car is, the last thing that he would have told you is you get somebody to pick up the wheel, to give it to somebody who gives it to somebody who puts it on the car. But that's exactly what we do with 3 levels of caches. We just stage it, and every time we pass the datum on to the next cache, of course, we consume energy again. Which brings me to the low power. Of course, I've got no great new architecture to present to you, but I can present some of the issues that I think might lead to really exciting new architectures. And one is when I looked into what is the theoretical minimum on power. And to my total amazement, the theoretical minimum for reversible computing, as I'm sure many of you will know, is 0. You do not need any energy at all to compute, as long as you can run it backwards, which is not surprising, because if you couldn't run it backwards, then of course it wouldn't be low power. So it just has to be isentropic. We don't do that. Of course, we throw lots of state away, we throw lots of bits away. So what's the lowest power if you do throw bits away? And the answer is something that was worked out in IBM research by a guy called Landau in the IBM Research Center in the 1950s. The price that you pay for throwing away a bit is 1k t log 2. So log 2 is roughly 1. K, of course, is Boltzmann's constant, so that's 10 to the minus 23. T is temperature in Kelvin, so you get 2 orders of magnitude there, so that's 10 to the minus 21. So you can throw away megabytes and gigabytes of things and still be in the sort of microjoules. So the theoretical limit for low-power computing is way, way off where we are at the moment. So there is enormous potential for improving the power consumption of processors. So one of the questions is the brain a good model? And one of the most exciting things I've been involved in just recently is organizing a seminar at King's in Cambridge with people who really understand architectures, like Stephen here, David May from Bristol, and a number of others. Were half of the people, and the other half were neuroscientists and biologists. And one of the people there was Simon Laughlin, a zoology at Cambridge, who told us that neurons are 100,000 times more energy efficient than computers at the moment. So they're doing something right, and that's worth studying. So hints from theoretical neuroscience, I think, are very welcome. Machine learning is something that we still don't do very well, and neurons do very well, and maybe Bayesian inference is the right hint there. But sort of my latest hobby horse that I hope to follow up is that maybe the key to understanding new computer architectures, especially when it comes to machine learning and organizing ourselves efficiently, are these shortcuts, these Kolmogorov complexity, for those that want to have a fancy name for shortcuts. And does that incorporate salience? And I couldn't resist putting this Ähnlichkeitserinnerung here by Rudolf Kahn up, because this is a book that I did an Arbeitskreis on, a sort of circle of friends that we had at Vienna University when I was a student. We read this book on the logical construction of the world, and the way you construct the world is with this wonderful, very short concept of Ähnlichkeitserinnerung that loosely translated is the recall of similarities, which our brain does spectacularly well. So in conclusion, I told you a little bit about the EDSAC, and you know, I am very keen to acknowledge the Manchester baby as well, of course. I talked to you about the 5 waves of computing, the clash between waves, ARM versus Intel, that the PC architecture has had its heyday, and that smartphone plus cloud is going to be the 5th wave of computing. But the brain is next, so thank you very much.